Okay, so we're going to look at this example problem here. You might want to pause the video and get the circuit copied down, and then once you got it copied down you can unpause it. So what we have here is looks like maybe a little complicated circuit. It's really not too bad when we get down to it. But one thing I want to point out here right away is that it looks like, well, we have a 500 ohm and then a 200 ohm resistor. You know, why do we have two resistors like that? They're in series. Why wouldn't we just have one 700 ohm resistor? And the reason is that I'm going to draw a little box here around this. This is my transformer. So we've taken it a step further here as opposed to just considering the inductors. Because transformers, if you ever looked at one, is a bunch of copper wire wrapped around typically. You know, even though copper has a low resistance, you know, you have enough of copper wire there wrapped around that you actually do get a resistance that's significant enough that you should account for it in the circuits. So in this case, we have a 9 Henry and a 4 Henry inductor, 200 ohm, 100 ohm internal resistors on it. So now when we're doing the circuit analysis, yeah, you could just combine those in series when you're doing circuit analysis. Alright, but before we do circuit analysis, we should convert everything into phasors. But even before I do that, one thing I should determine here is what is this mutual inductance. So remember, my equation for mutual inductance is K times the square root of L1 times L2. So this is simply just 0.5 times the square root of 9 times 4, which, if I can do my math correctly here, would be 0.5 times the square root of 36, which would be 3. And so then my mutual inductance would be 3 henries. But now we do need to convert everything to phasors. Now of course we know the resistors don't have anything change here in phasors. We're already given the voltage here. It's 300 at an angle of 0 degrees. So if we want to put that in rectangular, that's just 300 volts. And they do also tell us here that omega is 400 radians per second. So this should be kind of old hat at this point. So we have ZL1, which of course is just J omega L1, which would be J times 400 times 9, which would get me J 3600. And then ZL2 would be J times 400 times 4, which would be J 1600. Whoops, let's actually write 1600 down here. And then the last one, of course, that we need is this capacitor. So if I do the impedance for this capacitor, we know that that is minus J over omega C, which would be minus J over 400 times 1 microfarad, which gets you minus J 2500 ohms. So I'm going to go ahead and redraw the circuit here. I'm actually going to go ahead and pause the video while I redraw it so that you don't have to just sit there and watch me redraw it. Okay, so the circuit magically appears here. And you don't have to redraw your circuit, it's just because I don't want to have to keep scrolling back and forth when we're writing equations down. I would like to have the circuit just right here as opposed to having to scroll up and down. I did realize that there was one thing we forgot to compute here for my phasors, is we need the impedance of my mutual inductance, which is still, it's a J omega L because it's an inductance, and so this would be J 400 times 3, which would simply be J 1200 ohms, because we're going to need that as well. So my mutual inductance here is J 1200 ohms. And I know I've kind of squeezed everything in here to a smaller diagram. That's because I want to leave myself room for my equations. So we're asked to find I1, I2, V1, and V2. In general, for non-ideal transformers, you want to do loops. Because the reason you want to do that in general is that if you look here with this transformer, there's two loops. And if you wanted to look at nodes, there's actually a lot more nodes than that. Yeah, you can combine some things together, but trying to find V1 or V2, if you're trying to find those as a node, it's just going to become messy. It's much easier just to focus on the currents. Okay, so we of course have my current I1, and then we have my current I2. Now I'm going to go ahead and write down my mutual induced voltages here so I get the signs correctly. So I1 is entering the dotted side of the coil, so my induced voltage would be plus minus Vm1. And then on the I2, that current's entering the non-dotted side, so the symbol would be plus minus Vm2 with the plus sign on the non-dotted side of the coil. Alright, so then these were the equations we kind of had written up earlier, but let's go ahead and just start writing some of these here. So if I go into the minus 300, so I'd have minus 300 plus, I'm just going to actually write the voltages out here. So I'd have voltage across the 500 ohm plus voltage across the 200 ohm plus the voltage across the J3600 because my inductor, and then I'm hitting the minus sign of the mutual inductance, so I'd have minus JVM2 equals 0. And now what we're going to do is we're simply going to use, because we're in steady state, that V is equal to ZI for all of them here. Now you could have just skipped this step and gone directly to the V equals ZI, but I just want to emphasize we're just adding up all the voltages here in this loop. And so what we have here, well, if I substitute in here, I'd have, well, this would be I1 times 500 plus I1 times 200 plus, well, it would be I1 J3600 and then minus J, well, the impedance here, that's why we computed the impedance for this mutual inductance, so it'd be minus J1200 times I2. Because remember, that's the current, Vm2 is the current induced by I2, and we're entering the minus side of it. And so that's equal to 0. Then just simply cleaning this equation up, combining like terms, we wind up with 700 plus J3600 I1 minus J1200 I2 equals 300. And so this here is my first loop equation. So really shouldn't be too much difficult. The only thing you have to remember is always including your induced voltage here. Alright, now we have loop 2. Now loop 2 has no voltage source, so I'm just going to start, well, I guess I'll just start with the capacitor. And in this case, I'm not going to go ahead and write this type of equation down. I'm just going to go ahead and start with all the impedances. So the voltage across the capacitor would be minus J2500 times I2. Then I'm going into the coil, so that would be plus J1600 I2. Then I'll get the mutual induced voltage here, which I'm entering the minus side. So it's minus, now it's mutual, so it's the mutual inductance, J1200. And then it's Vm1, so it's due to the current I1. Now I got to finish it out here. I've got the 100 ohm resistor, I2, and then I also have the 800 ohm resistor, and that's equal to 0. Now, just like we did with the other equation here, we're just going to kind of combine terms together and get a simplified version. So we'd have minus j 1200 I1. And then if we're careful with the arithmetic, well, I have 100 plus 800, so that would be 900. Then I have minus 2500 plus 1600. So if I do my arithmetic correctly, I'm actually just going to, believe it or not, type this into my calculator. It should be minus 900. And yes, it's minus 900, so minus j 900 I2. And then here, and this is equal to 0. So here, star this is my second equation. Now, I actually already have the equations to find two of the answers. Two of my answers were wanting to know what I1 and I2 were. Well, I just set up my matrix. And the matrix we'd have set up, again, this is assuming you can't plug complex numbers into your matrices directly. We'd have, that's probably more space than I need. Well, that's fine, whatever. We'd have 700, 3600, because that's for this term right here. And then the off diagonal becomes negative, so I have negative 3600. The main diagonal stays positive, so 700. And then I just have, if I look at this term here, it's just imaginary, so the real part is 0. Then I have minus j 1200. And then this would, oops, not j, just minus 1200. Then again, the off diagonal, I switch signs, so I have positive 1200, and then I still have just 0 there. And then this final term, well, that's just completely real, so that would be 300, 0, and of course if you do the opposite sign of 0, it's still 0, and then 300. So that's my first equation. And then the second equation I'll write down a little bit quicker. You'd have 0 minus 1200, positive 1200, 0, and then we'd have 900, minus 900, 900, 900, and then my hand bumps into that again, 0. And so that would be the matrix that we put in reduced row echelon form. And so after doing the reduced echelon form on my calculator, I wound up with 1000, 0100, 0010, of course, and then finally 001. I didn't say enough zeros there, but then this would be 20.8 milli, and these are current, so I'll just go ahead and, well, I'll just write it as milli for now. M for milli. Negative 61.1 milli, 61.1 milli, 20.8 milli, and then 26.84. Let me actually write that a little bit better. 26.84 milli, 54.6 milli, and negative 54.6 milli, and I've been writing all of these in 3, so I'll just do that. 26.8 milli, and then this one would also be 26.8 milli. That's what my calculator gave me. So then what we have here is we have that I1 is equal to 20.8 minus J 61.1 milliamps, and I2 is 26.8 plus J 54.6 milliamps. And so if we wanted to, the problem asks for them in phasors. How do I know that? Because it asks for capital I1, I2, V1, and V2. So I don't actually have to convert these to polar form or anything. It's fine just leaving them like this. But you could convert them to polar form. We've done that enough times. I'm not going to do it. You know how to do that. But now we actually have to find V1 and V2. And I am going to scroll back to the original circuit here before we write the equation, because we have to think a tiny bit about V1 and V2 here. So what this is really saying is V1 is the voltage that is actually applied to the transformer, and V2 is the voltage that is on the secondary coil of the transformer. But it's not simply just the current through a single component here. Notice that you have two components here that make up the voltage loop for V1. You have the 200 ohm resistor and the 9 Henry inductor. Similarly, for I2, you have this 4 Henry inductor and this 100 ohm resistor. Or for V2, what I honestly probably would do is the 800 ohm and the 1 microfarad capacitor. The reason being is you have to be careful because of the entering the loops here, because your I2 would be entering the negative side of V2. So that means that my equation for V1 would be I1 times 200 plus J 3600, and V2 would be I2 times 800 minus J 2500. So if we do that here, we'd have V1 is equal to 20.8 minus J 61.6 milliamps times 200 plus J 3600. And I'm going to go to my calculator here to do that computation. So 20.8 minus 61.6 times, make sure to use parentheses, and when I do that, I get that this is equal to 225.9 plus J 62.6. I don't know why I put parentheses there, volts. And again, we don't have to put it in polar notation because it's asking for it in actually phasor notation. But I am going to go ahead and convert this to polar. Not because I want to, because I want to talk about something when we get the two voltages. So this would be equal to 234.42 at an angle of 15.4 degrees volts. And then V2 would simply be I2, which is 26.8 plus J 54.6 milliamps times 800 minus J 2500. Alright, so let's do that computation. And when I do that computation, I get that V2 is equal to 157.9 minus J 23.3 volts. And then I'm going to go ahead and convert that also to polar. And we wind up with V2 equaling 159 at an angle of negative 8.4 degrees volts. So what we should look at first off is this transformer is actually stepping down voltage. It stepped down 230 volts down to 160 essentially, or 159. And the other thing we should look at here, if I go scroll back up a little bit, notice here that I have 300 volts on the source, but that's not what is applied to the transformer. And that makes sense because of this resistor right here. That 500 ohm resistor means I'm going to be losing some voltage, and I'm not going to get 300 volts directly applied to the transformer. And we can see that by looking at V1. The voltage applied to the transformer is 234 volts, not the 300. Alright, so we're going to do one more video on this, and we're going to do that though dealing with ideal transformers.